Today we're going to be discussing single-phase rectifiers. The objective is to introduce the operation and analysis of single-phase low-frequency rectifiers. Specifically, we'll be considering the case where you have line frequency AC attached to a transformer which converts the AC into another AC voltage. This can be either a step up or a step down, or in fact it can be the same voltage magnitude, but just benefiting from the isolation that the transformer provides. This AC voltage is then passed into a rectifier, which rectifies our voltage into a noisy DC voltage. That noisy DC voltage goes through a filter and out comes clean DC voltage. So specifically, we're going to be talking about a full wave rectifier. And when you have a system like this, and you want to analyze it, as we do, it helps to break it down into individual equivalent circuits. So we'll go block by block through this system, starting with our transformer. So if you go back to your circuits class, you'll recall that the equivalent circuit for a transformer looks something like this. You've got a winding resistance and a leakage inductance. You have a resistor to model core loss and an inductor to model magnetizing current. This passes through to an ideal transformer stage, which has a turns ratio. And on the secondary side, you've got your winding resistance and leakage inductance again. So this equivalent circuit is still too complicated for the type of analysis that we want to do. And so let's focus on the section that we care the most about, which is this right here. And what is going on in this section? Well, we can view this as being a combination of a dependent current source and a dependent voltage source. So if the voltage that we apply on the primary side, if we call that V primary, on the secondary we have a voltage source that appears as N times V primary, where N is our turns ratio of 1 to N. On the primary side, we then notice an induced current, and this current is N times I secondary. I secondary is over here, and you can talk about the voltage output of the secondary as being over here. This entire diagram is in fact the equivalent circuit of the idealized transformer section up here. However, intuitively we know that this is not a complete model. This represents just this one component. And you can see this because as drawn right now, there's no connection on the secondary. The secondary is open circuited, which means that I secondary is always 0. If I secondary is 0, that means that N secondary is also 0, and therefore no current is flowing into the primary of the transformer. Intuitively though, we know that this is not true. If you attach a transformer with an open secondary, if you attach the primary of a transformer to an AC voltage source and you leave the secondary open circuited, a current will flow, and that current is a magnetizing current, and it takes a path like this. So in order to capture that information, we must actually add all of the elements that we have over here to our equivalent circuit. So we would then start to add our stator winding resistance, our leakage inductance, our network over here of the resistance and inductance, and so on and so forth. Adding all these resistances, inductances, adds complexity to your model. So when you're evaluating a circuit of a physical system, you need to take into consideration the level of complexity that you actually require. For our initial analysis in this class, we don't need to worry about these components. We can simply consider the dependent voltage source and current source model that we have right now. Moving on from our transformer, this was our transformer. Moving on from our transformer, we can start to talk about the rectifier stage. So if this model then continues out here, we attach it to our rectifier, and we attach that onto our filter. Okay, so I said we were going to be talking about full wave rectifiers. What is the equivalent circuit of a full wave rectifier? This also should be familiar to you from your circuits class. We can draw it as follows. You have 4 diodes that are connected to an input of some type. In our case, the case that we've been describing so far, this input is your transformer. The output of this continues on and is attached to your filter stage. We can label voltages and currents in this, and we'll be taking a convention of calling this Vs right here, the input to our rectifier, the current into it as Is, the current out of it as Id, and the output voltage as VDC. We can also talk about the effective voltage drop across each of these diodes as VD when it's conducting. Alright, so that's a full wave rectifier. Moving on to our filter. The filter can be composed of different elements. The simplest form is just a capacitor across the output. We can also talk about branches of LC filters, so inductors and capacitors. You can have many of these in series if you desire. And with each stage you add another order of effectiveness to the filter, so another order of purity for your output DC voltage. And finally, in our case, we're going to initially consider the load to be just a simple resistor. Okay, so we've talked about our transformer, our full wave rectifier, and our filter. Let's now consider the fundamental operation of the single-phase rectifier. We're going to lead into this by considering our single-phase rectifier to be attached to an ideal voltage source, Vs. Vs is assumed to have a peak of Vs hat multiplied by the sine of omega t. Omega is our frequency. We're going to consider the input current to be Is, the output current to be Id, and the output voltage to be VDC. So our task at hand is to determine the voltage and current waveforms and the average value of VDC. Let's start this by sketching our input voltage Vs. We all know what a simple sinusoid looks like, so that's fairly straightforward to draw. We can then consider the output voltage VDC. VDC is going to have the same value of Vs when Vs is positive, and the opposite value when Vs is negative. That is due to the connection of the diodes. When Vs is positive, we have a current that takes this path. When Vs is negative, we have a current that takes this path. So we can see from this that regardless, if we put arrows on this, regardless of the sign of Vs, Id is always positive, and regardless of the sign of Vs, VDC is always positive. So we'll remove these annotations and now sketch ID. ID is simply going to be VDC over our resistance RD. And IS is the input current, which we'll sketch in pink. It's going to be the same as ID when Vs is positive, but the opposite when Vs is negative. Now we're ready to calculate the average value of VDC. The average value of VDC can be found by evaluating this integral, 1 over the period of the quantity integrated over the period that it repeats. So if we perform this integral, we can quickly see that we actually only need to integrate a single half cycle. So if this is our period here of length t, we actually have a VDC waveform that's symmetric about t by 2. you have the same VDC waveform in this half cycle as you have in this half cycle. So we can evaluate this integral as being 2 over t integrated from 0 to t by 2 and integrated with respect to time. So if we evaluate this integral, it comes out as 2 over pi vs hat, which in fact is equal to 2 times the square root of 2 over pi times the RMS value of our input waveform. We're going to talk about RMS quantities later, but I'm sure you all are familiar with calculating the RMS value of a sinusoid as being the peak value divided by the square root of 2. In our next lecture, we're going to consider that in more detail. But for now, you can see that we get this average value in terms of either the RMS quantity or the peak quantity. And the job of our filter from our previous block diagram is to filter this noisy DC waveform to obtain a nice smooth average value as we're calculating here. So this shows the fundamental operation of the rectifier. Let's now consider a more complete system, and from the perspective of trying to design a converter. So here we're going to go actually from the transformer through a rectifier and output to a filter. So if we label on this diagram, the beginning portion here is our transformer equivalent circuit. And you'll see that this is much simpler than we had considered at the beginning of the lecture because we don't need the complexity. We're going to instead model our transformer as simply giving us an ideal voltage source and a series resistance. So basically we're making the assumption that the winding resistance dominates the inductance. Or in other words, we can say that R is much, much greater than omega times L. So if we have that assumption, and that's a very fair assumption to make for low power transformers, such as those used in wall-wart power supplies, for example, the charger for your cell phone. In these cases, the winding resistance tends to be very large because small wires are used, and there's a safety concern. If you have a short on the secondary with a large resistance, then you limit the amount of current, the amount of short circuit current that can possibly flow. So anyway, that is justification for why we were able to model the transformer as a voltage source in series with a resistance and no inductance. On the output of our circuit, of our system, we've got our filter, and we are going to model the filter as having an infinite capacitance. If the filter has an infinite capacitance, the voltage is fixed at a DC value. And this means that our load voltage is constant and our load current is constant because we've chosen to model the load as a resistor. Finally, in this example, we're going to consider the diodes to have a forward voltage drop of VD when they are conducting. So building off our discussion from last time, when Vs is greater than the output voltage, we are going to have a conduction path like this. When Vs is between the output voltage and negative of the output voltage, the diodes do not conduct, and instead we have a conduction path that looks like this. When Vs is less than negative of the output voltage, we can sketch a conduction path that looks like this. So if we put arrows on these things, we can again identify the direction of our current and sketch waveforms. To make this analysis simpler, we're going to try to sketch an equivalent circuit for when the diodes are conducting. When the diodes are conducting, you can immediately see that you've got your voltage source in series with a resistor, in series with one diode. You've got your load resistance. You have a second diode, and back to your voltage source. In our case, we're actually considering that our output voltage is fixed at a DC value, so we can instead just model this as a constant DC source of VDC. Remember, we said that each of these diodes has a drop of VD across it. So we can go from this circuit to a complete electric circuit, which has our input voltage, a resistance of Rs, and an equivalent output voltage of VDCE. VDCE is equal to 2 times VD plus VDC, our fixed output voltage. Now, how did we come up with this? Well, to drive a current through a resistance, our transformer output voltage has to overcome a fixed DC voltage. That DC voltage is the voltage drop across each of our diodes plus our fixed output voltage, VDC. And so we take this rather complicated circuit that we see on the top, and we reduce it down to this simple circuit right here. Now, this circuit doesn't apply all the time. This circuit only applies when the diodes are conducting. So you have to say that this circuit only matters when the diodes are on. So when that is the case, I can sketch this. And I see that I am in the way of my anticipated waveforms over here. So let's erase that for now. Okay, so we can take this a step further, and we can start to say what the value of Is is. So Is, or our input current, is equal to Vs, so remember this is Vs, minus our equivalent DC voltage divided by the resistance. And this is during conduction in positive half cycle. Okay, half cycle. What do I mean by half cycle? Well, if you go back to our previous example, this is a half cycle, and this is a half cycle. So positive half cycle refers to this quadrant, where Vs is positive. Negative half cycle refers to this region, where Vs is negative. So going back down here, we've got this expression during the positive half cycle, and we have the negative of it during the negative half cycle, during the conduction interval of the negative half cycle. And in between, we have no current. We have zero otherwise. What do we mean by that? Well, remember, we have this region indicated by this red line here. When the diodes are not conducting, Is is 0, right? All we're doing, the only current that's flowing is from our capacitor into our resistor. All right, we've constructed an equivalent circuit model for our rectifier. Let's now button up some details with regards to the current waveforms, the voltage and current waveforms. So previously we talked about the waveforms for a very idealized case. Now we're going to talk about these waveforms more in practice, and specifically we're going to define the inception time and extinction time of the current. So we'll start by sketching what Vs looks like about the time t equals 0. So this is Vs. And in this case, we are actually going to be assuming that this is a cosinusoidal current, so it peaks at time equals 0. So it equals Vs hat times the cosine of omega t. And on the same plot, we're going to show our equivalent output voltage. This is VDCE. And a graph of our current. So when Vs is below VDCE, we said we have no current. Actually, we're going to be showing the input current. When Vs is below VDCE, we have no input current. But as soon as Vs becomes equal to VDCE, we have a current that starts to flow because this equivalent circuit is valid. So this current is just going to appear as Is equals Vs minus VDCE over Rs. The time that this turns on is what we're calling our inception time, and the time that this turns off is what we're calling our extinction time. So since we know that Vs is a sinusoid, or in this case a cosinusoid, we can actually solve to find our exact inception and extinction times. Our extinction time is going to occur when our Vs expression evaluates to being VDCE. So you can solve this for the extinction time as taking VDCE, dividing it by Vs hat, taking the cosine inverse of this quantity and dividing that by omega gives you your extinction time. Your inception time is simply the negative of the extinction time, because a sinusoid or a cosinusoid is symmetric about time t equals 0. So therefore, Ti is equal to the negative of Te. And this concludes our basic analysis of the operation of single-phase low-frequency rectifiers.